Okay, so stopping the world exploding using consumer-driven contracts. So you've all seen that slide a million times. This time it says I've built systems that have been prone to explode. So I suppose the motivation with this talk is the very, very obvious fact that we've all been here. We've all built connected systems. In the 2010s onwards, everything is connected now. I'd be very, very surprised if you're building a system today that doesn't call one or more APIs or other dependencies or databases. You know, if you're the one guy with that one job who gets to write little code in a little box of isolation, then where can I apply? That sounds like heaven. It sounds lovely, but it's not reality for most people. So we have to rationalize the fact that building systems in an increasingly connected world is really difficult. Systems fail. Systems go down. Systems change. It's unpleasant. And other people's changes can completely ruin your day, break your ecosystem, ruin your code, and at the end of the day, negatively impact your users. The systems might not even exist when you're trying to build code that integrates with them. And it's funny because people don't often think about this, but if you sit on the bleeding edge and you're starting to adopt new technologies, you're building against shifting APIs, shifting web services. All this kind of stuff is so uncertain that it's very, very easy for you to look at the problem and say, oh, well, I can't do any work yet. I can't do anything now because the system I'm building against isn't here. It doesn't exist. But unfortunately, again, in the real world, that's not how we ship code. We have to continue. We can't just wait and burn money and time and resources for someone else to be ready. Or perhaps you have the misfortune of working with an unreliable partner. Go on, any guesses for the visual pun? It's Ashton Kutcher, and he cheated on Demi Moore. There we go, see. Nobody reads the Daily Mail.
No.
Neither do I, actually. But
I used to work on Heat, don't forget that.
Oh, of course. Well, there's no more celebrity puns for you in here. Or you have flaky hardware. Hardware fails. Everybody groans. Hardware fails. This is reality, especially if you're not cloud hosted. So if you're not cloud hosted, what you end up doing is you have infrastructure teams and DBAs and operations people who are human points of failure. In a cloud environment, you get a different kind of fickleness, where because there's such a huge amount of kit running and scaling over huge amounts of availability zones and computers and data centers, actually small blips are quite common because data centers can drop in and out, or maybe a rack dies. You might not think that that means it's down, but your app will still encounter this kind of stuff. And it seems like it's impossible to isolate yourself from Professor Chaos from South Park. But the truth is, this is actually a good thing. We're in a better place than we were in the 80s. And it seems like I've just said, all of this change is horrible and it's bad, and oh my God, it's risky, and everybody can ruin my day. But the truth is, because of these APIs and these outsourced services, we can build more software better and faster than we ever have been able to before. Like one person could be amazingly productive in an API-driven ecosystem, whereas before you kind of had to build the world to ship software in the 90s. So let's talk about failure. The first time you know that a system you depend on fails is often when you have a user in the real world using your software, making it fail. That's the latest possible time that you can discover that something you depend on is down. Normally, because something fails and then they call up really, really angry and shout at somebody, and then that person gets out your corporate phone book and looks up the person who they're going to call up and shout at, and then everybody feels really terrible because all that's happened is loads of people have shouted at each other. Then you have to work out what went wrong. That's a really, really terrible place to be, and it's the default for a lot of organizations. If you're a mature organization and maybe you practice DevOps as a culture and you have first-class monitoring and alerting, then maybe you actually know. So instead of somebody calling, a user turns up and they have a terrible time because some API you're calling is down and your pages crash, and they care about it enough to call. I mean, they may not care about it enough, and it might be the 100th user that cares about it enough to call. If you've got monitoring and alerting, maybe they don't need to call, right? So you know that a little alarm goes off somewhere, but you're still fundamentally reactive. the thing that's bad has already happened to potentially quite a lot of people.
Question.
Yeah.
Did you deliberately pick a picture of a cat with heterochromia?
No, I didn't, but that's really cool. I didn't even notice that. I was not alert in selecting my alert cat.
Or might be a Bowery pun.
So, for instance, Kibana, Logstash, Elasticsearch can help you diagnose a problem, but it's already affected everybody. This is diagnosis. This is the start of resolution. It doesn't tell you that something's wrong. Something is wrong. It doesn't warn you. So somebody's already having a poor experience with your software, and that's what you really want to avoid at all costs. You want to stop the users being angry because they're the people that pay and come back and make money. So what we really need is a canary in the coal mine. So are you all familiar with the term canary in the coal mine? No? Okay. So back in the times when coal was mined by people that looked like that and photos were black and white.
The 70s.
The 70s in Sheffield. That was steel. But, when carbon monoxide rose too high, I think I'm correct here, in the mines, miners would get sick and die because you can't smell it and it kills people. It's the same reason that you have carbon monoxide detectors in your house today that you can stick in your kitchen. Scentless gas that can kill. So they used to take canaries into the coal mines because canaries are small and they die quicker. Simple as that. So we need something that will die quicker than our user experience. It's actually really bleak when you think about it. We're just murdering hundreds of birds, but to save people. So we want to save our people by murdering other software. Ultimately, a system deliberately and meaningfully disabled is better than a crashing one. So if your system is ostensibly up, that perception of upness, phrasing, is important. You know, it's funny that doing simple things in a production environment, like say your database goes offline, redirecting to a holding page that has the look and feel and style of your homepage will stop people ringing up and complaining, because what it says is that we know something is wrong. You've got this thing, it looks real. Maybe you've got a Twitter feed on there that's got a bit of feedback on it. People don't go mad because it looks like you're under control. If your database falls over and you respond a bright yellow or bright white error page with a stat trace, the internet is ablaze with the fact that you are down and you are failing. You failed in exactly the same way, but perception really is everything. So disabling your system knowingly is always more important because that's you being responsive and proactive rather than just responding to the chaos that's happening around you. So consumer-driven contracts are a technique that we can use to give us a canary in the coal mine. This is our sacrificial piece of software that will die first, ideally before our production systems do. So like everything with a sciencey name in programming, we get to invoke Martin Fowler. That's a pentagram of protection. Everybody thinks it's some evil, demonic thing. It's protection from bad. So the good thing about this is actually super, super old news. So back in 2006, Ian Robinson and Martin Fowler. So Martin Fowler is, I believe, the chief scientist at ThoughtWorks. Ian Robinson used to work there. He now works for Neo4j, I believe, doing graph database things. Everybody's doing graph database things. But they put together a good long read called Consumer-Driven Contracts, a Service Evolution Pattern. And they outlined and defined a pattern called consumer-driven contracts to help mitigate against what they saw as the rising tide of risk in at the time new SOA designed systems. So in the early to mid 2000, before we rebranded them as microservices, SOA was all the rage. So building loosely coupled systems using normally SOAP APIs to interact. But ultimately the failure pattern is the same. You've got two things that communicate over a common protocol, and there is a connection failure, and one of the systems is the victim and one of them is the source of the failure. It's a great piece. I'm going to summarize it here. It's a good read, but it's a bit sciencey. So let's read the science, people. There's Martin Fowler chatting to you. So the consumer-driven contract pattern recommends building service communities using consumer and consumer-driven contracts. This pattern does not, however, specify the form or structure that consumer and consumer-driven contracts should adopt. nor does it determine how consumer expectations are communicated to the provider and asserted during the provider's lifetime. Contracts may be expressed and structured in several ways. In their simplest form, consumer expectations can be captured in a spreadsheet or similar document and implemented during the design, development, and testing phase of a provider application. By going a little further and introducing unit tests that assert each expectation, we can ensure that contracts are described and enforced in a repeatable, automated fashion with each build. So basically, they define the characteristics of consumer-driven contracts as closed and complete, singular and non-authoritative, with bounded stability and immutability. So we're going to go into their literal definitions, and then I'm going to try and explain it in a little more plain terms. So closed and complete means that a consumer-driven contract is closed and complete with respect to the entire set of functionality demanded of it by its existing consumers. The contract represents a mandatory set of exportable elements required to support consumer expectations during the period in which those expectations remain valid for their parent applications. So that's a real big mouthful. What that really means is, from the perspective of my application, here are my expectations of the service I consume. So a service will have a service contract, which will say outline 100 functions that it provides and exactly how they work. Your application may use 3 of them. So the consumer-driven contract perspective on that is, I don't care about all 100 things as long as the 3 things that I care about work exactly to specification. You can break everybody else's universe for all I'm concerned. Please make sure what I have work. Singular and non-authoritative. So provider contracts, the system at the other end, are singular in their expression of the business functionality available. So that means there is one contract for the service you're consuming that says everything. But they're non-authoritative because they're derived from the union of existing consumer expectations. So that's a bit of a mouthful, and we'll dig into that in further slides. They have bounded stability and immutability. So a consumer-driven contract is stable and immutable in respect of a particular set of consumer contracts. How meta. That is to say, we can determine the validity of a consumer-driven contract according to a specified set of consumer contracts, effectively bounding the forwards and backwards compatible nature of the contract in time and space. The compatibility of a contract remains stable and immutable for a particular set of consumer contracts and expectations, but is subject to change as expectations come and go. The one-sentence version is your consumer-driven contracts change to reflect your changing needs of the systems you depend on. So the great thing about having really good formal specifications around this is they really covered all the edges off. Unfortunately, I think that while Fowler and Robertson's piece is really good and definitive, I think it's really unapproachable and terse and difficult. I mean, these were just some snippets of the original piece, and it's quite hard to translate that to real things that people can do, real advice. So that's enough plagiarization for one day. I'm going to stop copying and pasting Martin Fowler, however much I think he's awesome, by plagiarizing The Simpsons. So a consumer-driven contract is a set of expectations from the perspective of your consuming client on the systems it depends on. And there are no rules. The nice thing about it being so meta is actually a consumer-driven contract, ideally, is anything you can use to verify the state of this dependent system. And we're going to go into what I think a good way of approaching this is. So CDCs could be a spreadsheet of operations and expectations. So that's kind of okay, right? It's fine, it'll work. So every time you're about to ship some software, you open up your big old spreadsheet and you check everything. Cool. A set of schemas to validate. So this is very much from the school of XML and SOAP, where XML web services would provide XML schemas, and you could literally validate that there have been no changes against a certain set of requests. So you have a list of things you depend on and their schemas, and you check that they match. It's fine. A point-in-time hash of a known set of data. So maybe the service endpoints and the boundaries and the service definitions, you can hash into a magic number that then you can make sure doesn't change. Or, and most importantly, as far as I'm concerned, real live API calls against known data. So this is where the real magic happens, in my opinion. Let's focus on executable things, because executable things are real and tangible, and they're not meta, and they're not formal language, and they're not specifications. They're things that people can touch. So CDCs are valuable, in my opinion, at 2 points in time. Firstly, during the development of new code, and secondly, during the ongoing operation of a system. So actually at the start, I was saying, oh God, this isolates you from change. It gives you early warning, what a canary in the coal mine. Actually, it's just as useful when you're building new systems. So as with every kind of test, you have to work out what the benefit of the test is. So I presume some of you here will have written smoke tests before in your life, just things that test systems occasionally. Check that the system is working. So a CDC would look actually quite similar to a smoke test. So during development, let's talk about them during development. And that honestly is like the second Google image search for programming, because people are crazy.
We use that for the hackathon, on Facebook.
Yeah. So CDCs during development are the best way to help isolate you from a brittle system that you're building against while ensuring correctness, but they're part of a pair. So a CDC goes alongside a stub. So we should basically stub all the things and blind everyone with a white light in the room. They should be paired with meaningful stubs of the API calls against the services that you're building against. So the idea is that you build against stubs that are verified by your CDCs. So an executable CDC makes a call with a known response against a target system. These known responses are captured and used to build stub services that are stable, immutable, and known. Your developers can then point against them and be isolated from downtime and brittleness in the target system. So a meaningful example, if you're working with a partner company who's building a new API for you to consume, and they give you access to a pre-release test environment, and every time they make a code change, that environment goes down and comes back up 5 minutes later, that will cause you nothing but pain during your development cycle, because you will permanently never know whether the code that you're writing is broken or their environment is just down briefly. It's a rubbish, unknown way to be. So by writing a stub based on a known expected set of data from their environment, you can develop in isolation while simultaneously executing and verifying the tests against their environment. So your stub should present the exact same API along with matching protocols, URIs, and responses. Obviously, there's a little bit of subtext here, which is presuming this is a HTTP thing. There are other ways to approach non-HTTP stubbing and mocking and verification, so maybe schemas are a better fit there. The truth is, in the world that we're in today, the vast majority of integration points that you'll find yourself building against are going to be HTTP. Potentially a benefit, really. So during operation, CDCs in production, firstly, should be the same as the ones you use in development. They are regularly run tests that verify the correctness from your application's perspective of a system you're integrating with. So a real tangible example would be, if you're working in C#, a set of NUnit tests that call the exact portion of code that interacts with the system and asserts both on the format and the data returned from a known API call. So you have that, and then you run it using your CI environment every 2.5 minutes, every 5 minutes, and you do it in development. So you permanently verify the upness of your development environment. And then you make a second configuration that permanently verifies the upness of the production environment. And you have two big traffic lights then. So given a system that does CRUD, a CDC could be as simple as an integration test that creates, retrieves, and deletes a record. And actually, the interesting thing is, again, you're only dealing with a subset of the API of the system at the other end. So if it provides 100 methods and you're only using 3, you could even get really, really small and say, actually, for the first method call, Say it brings back a name, an email address, and an ID. If you're only using the ID in your system, only assert that the ID comes back in the place you expect it to be. Who cares about the rest of the data? If they break the rest of their system, but they don't break the ID that you rely on, okay, we're golden, we're happy, we can still ship, still works. And that's the level of certainty. It's the real smoke test of, can I ship this code? So the value of CDCs are realized when you execute each and every call that your client application makes against the target system. If you leave a gap, you can miss a breaking change. So this is a really, really good way to build SDKs out. So if you're building an SDK, and I would generally recommend if you're connecting to another system, you have something that at least represents an SDK, even if it's just a single class with a single method that says get data from other system. That is an SDK that your system's using. You take that and you execute it outside of the context of the real system in a test, again and again and again and again. But it's important that you get a full coverage of all the method permutations that you use. Otherwise, again, there's an area of your mind where the canary's not present and wouldn't die if it broke. And obviously, CDCs and stubs then go hand in hand. CDCs verify expectations against the target system in a given environment. And it's the combination of those two things. A target system in an environment, and the subtext there is, and a specific version. So they're very much point-in-time snapshots of expectations. The stubs provide a known stable mock of that exact verified expectation. The CDCs and the stubs, as a result, must always be in sync. So it's important that your stubs present the same sample responses that match the assertions of your executable CDCs, to the extent that if I took those tests and pointed them at the stubs, everything would be fine, because that's the level of kind of symbiotic relationship between those two parts of the same thing.
So it's just two classes that implement the same interface.
Exactly that, right? One tests it, one returns some data, and it feels really, really synthetic until you point it at something real. So you have a test that tests my SDK brings back the right data, but that's real. It touches the actual partner system. And then you should be able to change the URI of that partner system to your stub, and everything would pass. Like it's important, because what that means is you can change those two things in isolation. Because if the stub wouldn't pass, at that point that means that you've broken something. And if the partner system goes down, you can still build, but you can't ship. So you get that early warning sign immediately. And in a production environment, actually, what you tend to find is it serves a better warning than alerting and logging, because it happens immediately if you get your frequency up. There is no reason, if the partner system can cope with it, you could not run them every 30 seconds, every minute. And generally, so on a really high traffic site, what you'd find people saying is, oh, well, this isn't the only way, actually, because we can deploy to 10% of our users and we'll just monitor it. And because we have so much money and so much traffic, that's actually okay. It's fine, because if 1% of 10,000 users that arrive a day have a bad time and we can fix it in 5 minutes, we don't really mind. That's a nice problem to have, because you've got a lot of money and a lot of users and a lot of monitoring and alerting. This is something we can do as developers, where maybe we have a couple of thousand users a day. And maybe instead of having a cheap commodity product, we have an expensive product that fewer people visit, but they pay more for. So the disruption of 1% of users is really super disruptive. It's the SLA thing. If you should always be aware that, what does 5 nines mean to you? Does that mean 200 people a day have a terrible experience? If that's what it means to you, if 3 nines means 2,000 people a day have a terrible experience, and you're willing to let these systems break, actually that loses you real money. That's meaningful and loses you money, and you should try and avoid it. So I'm not saying that this will stop you losing money, because the truth is, when your CDCs fail, what that means is your real systems are failing right then, because they simulate exactly the same failure conditions. But it gives you that head start in the race to the mean time to resolution. So you're not waiting for the half hour later when the 2,000th person decides he's had enough and is going to call up, for then support to escalate through first and second line, for it to arrive at a developer to start investigating. At this point, we've lost half a day. That's rubbish. That's not responsive. Obviously, bigger organizations, bigger monitoring, bigger teams, sure, maybe you've got devs that are really, really on the ball, but unfortunately, not everybody has exactly that kind of setup. So this is something that kind of works for everybody, and more importantly, can work up front in development. So it's a tool for building, and then it's a tool for maintaining and monitoring. I like that cartoon on backwards compatibility. It made me chuckle. So CDCs also have a secondary benefit of helping verify the forwards and backwards compatibility of target platform changes. So in a mirror of that, your stubs act as a verification of forwards and backwards compatibility in your consumer code. So it's a great way to kind of test drive changes to contracts. Oh, I changed the contract. Did the code still work? Cool, we don't have to do anything. Problem solved. Our code wasn't brittle and bound to implementation. It was fine. But you could use it as kind of a guide at development time to see how you could evolve services in a backwards and forwards compatible way, and you could work out exactly how much code you need to change without having to go through the effort of changing external systems. The nice thing is I've been talking about this mostly in the context of an ecosystem of systems that you don't control, but it absolutely applies within an ecosystem of multiple teams in a single organization building software for each other. Because ultimately, if you're doing that and you're building strongly defined contracts between teams, you should be able to behave and operate as if they are completely separate companies by people you don't know just delivering a product. And what that means is you're exposed to the whims of those other teams without potential communication. And ultimately, I suppose what you could really see a consumer-driven contract is a crutch to get over the fact that conversations don't always happen during change. So yes, in a perfect world, you use vendor A. Vendor A would give you 3 months written notice of any change to a published contract and specification of the behavior of their service, and you would have time to adapt. Great, you're good, you feel golden, until vendor A's infrastructure fails and they go down anyway. So it's worth understanding this, and it helps you build code that prepares for failure conditions, because given a stub that works, you could actually simulate failure. You could say, okay, well, let's write a stub for what happens when the service is unavailable. How does my code respond? So normally, if I said that to a regular developer, oh, I want you to write a test for when that server isn't there, in an integration environment, they start going, oh, well, we don't really have any components. Do we need to block some ports? Or it gets very, very complicated very, very quickly. If you bring the conversation down to, we have these known stubs and known contracts here, implement a method in here that when given a specific parameter, it times out. Now write some code to cope with that. You've got a real measurable piece of software you can use to drive these kinds of tests and learn how to make your code more resilient. So how can I build CDCs and stubs? Yeah, the simplest way is to invoke the portion of your client code with some known data and write assertions on the results. That's good enough. If you're doing something with XML, firstly, I'm really sorry. Secondly, use any schemas published to verify them. If you're building SDKs, invoking SDK is the simplest way forwards. Building stubs. So luckily, the vast majority of APIs you build against will be served by HTTP, and intercepting HTTP requests is easy and something we do every day. So tools like Fiddler can sniff response requests. If you've got some Ruby foo, there's a really amazing Ruby gem called VCR, which is an intercepting proxy that you can configure to intercept a call, and it will record all the response and requests and headers, and it'll save, I think it calls them cassettes, so you can have pre-made stubs based on exact requests that you make. Isn't cassette a CSS bundling and minification library? Or are there now two called cassette?
Something else.
Cool.
Looked at it very briefly.
I know I built my own intercepting proxy that I called Puppet Master at one point, but this is quite easy to do. You know, the simplest thing you can do is capture a sample request and response call from an initial spike or a prototype against the third party, save the responses to disk, save a flat file, and then bootstrap up a microservice that returns these exact known responses. So if you've never done that before, it sounds quite hard. All we're really talking about is making an executable thing in your solution or your source control folder using a micro framework like Sinatra, Nancy, Express.js, the Play framework, Drop Wizard, all of these really, really popular micro frameworks. I mean, maybe I will run a workshop like with a meaningful demo of exactly how to do this against a real thing. But we're talking, you'll need to write about 6 or 7 lines of code to do this. So it's really, really easy, really accessible, and it just solves a lot of problems really quickly. And then you run them all the time. That's the most important thing. So CDCs are a vital part of your continuous integration strategy. You should be running them all the time against every environment you use, and using your CI server as a build runner. Run them quick, run them often, and you'll get the fastest response time that you possibly can. So to summarize, with CDCs and stubs, you can develop without friction because you don't have a moving target to build against. You can use failing CDCs as a conversation starter with other teams or companies or partners. So if something was working and started failing, you no longer end up in a he says, she says about whether their service has changed or works. You can say, look, I've got these tests that were verifying correct. Now they are verifying failure. You didn't tell me. Please, can we have an honest and open conversation about this? You can use them to measure expected performance. It's a nice side effect. There's no reason you couldn't put performance metrics around the running of your CDCs so you can know what the expected performance characteristics of the third-party systems are all the time. So you could measure those changes in test run times. So I've done that to pretty good effect when we had a partner company once in a previous position where they basically ruined their performance by releasing some code, and they absolutely refused to accept it until we gave them empirical evidence that proved that they had. And yeah, knowing when things will fail in production before the user finds out is obviously the thing that we really want to do. So there's an optional demo that I'm not going to do. I probably do have the time, but I haven't prepared it yet, which would walk us through taking a service, capturing the responses, and building a stub and running a CDC both against the stub and the service. So when operating real software in production, knowing what the users are going to experience before they do it gives you a head start in the race to the mean time to resolution. Brittle systems occasionally. You can build code in human systems and degrade your application in a knowing and meaningful way. So CDCs will give you the extra visibility. In a connected world, the way people perceive the systems that you build and operate can be inadvertently damaged by your downstream partners. This is the world we live in today. This is factual. The best thing we can do is react. So you can't control it, but you can mitigate the damage. And I'm done. Any questions?
That's a question and a point. Sometimes when you're consuming a third-party service and you're paying for that service, you're paying per API call, or you have a limit on the API calls that you can make.
It's a good question.
Google's geolocation being a classic example. So if you've got a test that's running constantly in the background, eating up your API calls, it can actually start costing you money. Correct.
So that's okay though. So what we're doing is we're paying for visibility.
Well, it is okay.
You're right though. It's a meaningful concern.
It's an issue you need to think about because quite a lot of people will take advantage of the fact that providers like Google will give you a certain amount for free.
Yeah.
But when you go over that limit, then suddenly they want a lot of money.
And you don't want your tests.
That's the difference between a business surviving and a business failing because it can't afford to pay the bill.
You don't want your tests to destroy your production environment. That's literally the inverse of what you're trying to achieve. So, I mean, the simplest answer is the obvious one here, I think. And if that's the case, you need to reduce your frequency.
You do.
And that's really meaningful. And yeah, I might actually add that to some of the slides. That's a good point. Anything else?
And about David, because we are expecting that we can use the stubs always getting the same data, and in this way we can test our parts. But about comparing the response from the production from the third system, eventually in the true world data can change. Eventually Google can about the geolocation can I don't know have a better precision and change something.
So you're talking about data, right?
Yes, about the data.
Yeah, so you might find that the tests in different environments assert on different data points, but the structural tests and the tests of the communication between the systems are obviously the same.
Yeah.
Okay, so you can test the structure and not the data, comparing the data of the stubs with the data from production.
Yeah, and bear in mind that it's okay to make fake data in a production environment if it gives you decent clarity on assuring the upness of your system. There's nothing wrong with a test page, right?
You can test the shape of the data rather than the value of the data.
Exactly.
So, you say, I expect these two things to be geographical coordinates.
Yeah.
Well, as long as they look like this, I know they're a coordinate and not something they've changed it to.
Exactly that. So you may find you're in a world where you're effectively doing schema validation. And, we're approaching a place where JSON has schemas as well today. Whether you want to use that, again, remember the key tenet is we don't care if they change anything but the thing we rely on. That's the important thing. It's about that critical path of we need these things. Let's verify we still get them. Oh, look, they changed every other single thing about their entire business, but that one part of data in that API still works. Then I'm happy because I'm still up.
A lot of this seems to focus on like external APIs and systems and stuff. Is it something you should implement on just internal systems?
Systems you don't control.
Okay, so if you technically all in the same company and do control them, then you don't
Nope.
really need to implement this.
Well, put it this way, if someone calls you and says, fix your system, if you can exert the ability to fix the system, then you're probably okay. If you have to escalate to 4 other teams and make 10 phone calls and get people out of bed, actually you should have probably designed for failure there, because you can't control the resourcing of those people. You don't know how responsive they're going to be able to be. So you want to design a system that gracefully degrades if their components are offline, because you can't fix it. And generally, imagine everybody's on holiday, or it's the weekend, or there's a company away day. This is a way to drive out the kind of design and systems where first we get an alarm, but secondly, because we're built in a way that we're aware that things can go down, we build in failover and maybe defaults for disconnected or lack of availability, or we toggle off features. It influences the design of the rest of the system to add more, I suppose, capabilities for other systems and components being down. So CDCs are not the whole story, they're just the start of the story. So what you get from the CDC is the red light when something went down before a customer phones you up. What you get from the stub is the ability to isolate yourself from developing against brittle systems that aren't ready or are flaky or maybe down. What you get from designing in that way is the knowledge that you can then control tests that simulate disconnected systems. And from that, you're able to write code that responds more appropriately to systems that are offline or disconnected. So it's part of a journey, but they're kind of the first piece in the corner.
Okay.
Awesome. That was great. Thanks, guys.
Thanks.
Let's try and hang up on all the people on Hangouts.